What we were trying to do is understand these two classic papers of Maxime Kontsevich. Actually, we weren't nearly that ambitious. We were trying to understand theorem 1.1 and spend a year, and I think we actually understand theorem 1.1. So my goals for this talk are to give an elementary description of the basic constructions in the proof as we understand them. I'm a little worried that many people here understand them better than me, but I want to explain. So after I do that, I want to explain how there was a difficulty we came to in the proof, and which Kontsevich did resolve, but it leads to nice algebraic structure on these. Oh yeah, I forgot to say what theorem 1.1 was. Maybe I better put it back up. So what's the point of theorem 1.1, and why was I interested? Theorem 1.1 is computes the Lie algebra homology of three infinite-dimensional Lie algebras, and the answer comes out in terms of well, there's three homologies, so there's three answers. The first one is gives you Kontsevich's graph homology. The second one gives you the cohomology of mapping class groups of surfaces. And the third one gives you the cohomology of outer automorphism groups of free groups. So this is a group that I've been studying for a long time. In particular, I've been studying its cohomology, so I wanted to see what this point of view had to say about cohomology of this group. So that was how I got interested in this. Right, so these are my three goals. Explain the difficulty and how he gets some nice algebraic structures. My third goal is to end on time. So I'm probably not going to get to the third topic in my talk, which was automorphisms of free groups, in fact. But I actually just finished a survey paper about outer space, in case you know what that is. It's how you study outer automorphisms of free groups. The connection with what we're going to see is outer space is a space of graphs. And the group of outer automorphisms of the free group acts on it, and you use it to compute cohomology of the group. So those of you who know about graph homology can see immediately that it's got something to do with graphs. You've got a space of graphs. Probably going to use graphs to compute homology. Okay, so I want to start by describing these three infinite-dimensional Lie algebras. There's that occur in this theorem. There's C infinity, A infinity, and L infinity. C is supposed to remind you of commutative, A for associative, and L for Lie. And they all have definitions in terms of derivations. You take a free X algebra where X is commutative, associative, or Lie, but you don't stick in the unit if there is one. And then you look at a certain subset of derivations of A. Maybe this isn't quite precisely correct, but you look at derivations of A, and then there's a natural bracket of reversing the order of composition. And so that's a very easy way to define what these things are, but in order to understand what's going on in the paper, you have to reinterpret these things in terms of Lie algebras of decorated trees. See? Okay, right, these Lie algebras that I had up here, they're limits of Lie algebras, one for every n. Oh, I see. Okay. It's okay, I can move the slides. I'll do it. Right, so this commutative guy is what's going to end up giving you graph homology. The associative one's the one that's going to give you the cohomology of mapping class groups, and the Lie one is the one that's giving you the cohomology of outer automorphism groups and free groups. I'm going to actually stick to the commutative one for this talk most of the time because it's easiest to describe, but I'll show how everything else just goes through. So I'm going to give you a basis for the commutative algebra, Lie algebra. Well, the way I'm going to think about it is you look at trees. They've got one vertex, and they're decorated with labels from the set P1 up to Pn, Q1 up to Qn. That's where the n is. And there's this operation you do on trees, on decorated trees. If you have a Pi on the left and a Qi on the right, you can smash them together and you get rid of the red edge, and you get a new decorated tree. If you have a Qi on the left and a Pi on the right, you smash them together and you get a new decorated tree, but you put a minus sign on it. And then you define the bracket of two decorated trees to be just the sum of all possible smashes. You look for all matches of xi's and yi's, smash them all together, and so on. So this is really just a graphical way to describe a Poisson bracket of polynomials. I've done an example up there. There's a what is there? There's a P1 I can match with a Q1. That's the only things that match. So I smash them together and get that. And if you compute the Poisson bracket of those two polynomials, you'll get that answer. Okay? So since it's Poisson bracket, we know it's a Lie bracket. It's actually a fun exercise. Well, it's an easy exercise to prove the antisymmetry in Jacobi relations just graphically.
What is Poisson bracket?
Oh, the sum of ddxi, ddpi, ddqi minus ddqi, ddxi. Okay, so that describes this Lie algebra. In the case of associative algebra and the Lie algebra, instead of using these trees are not embedded in the plane. They're just trees. And so if you want to describe AN, what you do is insist that the trees be embedded in the plane, which is equivalent to giving a cyclic ordering on the edges of the tree. And then the smash, well, if you smash two things that are ordered together, there's a natural cyclic ordering on the result. So that's what you use to smash, to define the bracket. And in the Lie bracket case, you use trivalent planar trees. But you have to be, this is a little bit more of a challenge here because there's an equivalence relation on planar trees. There are equivalence relations on planar trees that come from the antisymmetry and Jacobi relations in the Lie algebra. And I've been to a lot of talks today, but somebody already did this. I don't remember who it was. So, was it? Okay. Okay. So the way you smash two trivalent trees together is you stick them together, but you don't actually smash the edge to a point. You leave an edge there because you want to end up with a trivalent tree. So with all these smashes, you define brackets as the sum of all possible smashes with signs, and they form Lie algebras. So the theorem was about the homology of a Lie algebra. So how do you compute the Lie algebra homology of a Lie algebra? Well, you take the exterior algebra and you define a boundary map, which I've written down up there, You take the I and j guys out, bracket them, put them in the front, and add a sign to make everything work out so that boundary is 0. So that's what we want to compute. One thing to notice is all of these, well, Cn contains a copy of the Lie algebra sp2n. You can identify, in fact, sp2n with the subalgebra consisting of trees with exactly 2 leaves. If you smash 2 of these together, you're left with another tree with 2 leaves. So, in fact, that forms a subalgebra which is isomorphic to sp2n. And also, the cyclic ordering doesn't matter much around the vertex. You can think of that as a planar tree if you like, or you can think of it as a trivalent tree if you like. The point is that the an and ln also contain copies of the same thing. Okay, so we have this Lie algebra, this chain complex that we want to use to compute the Lie algebra homology, and it's easy to check that this boundary map restricts to a map on the sp2n invariance of this chain complex, and it's a fact that you can compute the homology of this chain complex by computing the homology of the subcomplex of invariance. It's a fact from homology of Lie algebras, homology of Lie algebras. So you want to understand these invariants in Cn. This is a very quick tour of the graph of the proof. Here we go. Okay, so I claim here's a way to get an invariant in Cn. I start with something I'm calling an oriented graph with K vertices. So what do? I take a graph. I'm supposed to order the vertices, like that maybe. I'm supposed to orient the edges. And on each edge, I'm supposed to stick a pi and a qi. Like maybe p1, q1, p2, q2, and maybe another p1, q1. Okay, so now I have a labeled oriented graph, and I want to get a wedge product of things. Around each vertex, I have a monomial. So what I just do is I have 2 vertices here. I'm going to get 2 monomials. What do I have? q1 squared, p2, wedge p1 squared, q2. So whenever I successfully label a graph, I get an element of the exterior power. And it's clear that some things give me equivalent elements of the exterior power. Like if I numbered the vertices in a different order, I would get plus or minus the same invariant. Oh, wait a minute. Sorry, I haven't gotten invariant yet. Forget it. So far, I just have an element of the exterior algebra, exterior product. Now, given an oriented graph, I'm just going to label the edges and label the vertices and orient the edges. I'm going to get a sum of terms. I look at all possible ways to order the edges with pi's and qi's. So there are 2n to the number of edges ways of doing that. So I'm going to get a sum with 2n to the e terms. I wedge all these monomials together, and I put a sign. Depending on if it's this kind of an edge, I get a plus sign. If this is kind of an edge, I get a minus sign, and I multiply them all together, I get a sign. So this gives me a recipe. Given a graph with ordered edges and ordered vertices and oriented edges, I get a sum of terms in this exterior power, and it turns out that it's an invariant. That's also fun to check graphically. Here it's clear that if I change the labeling, if I change the numbering of the vertices, I would get the invariant would only change by a sign. If I change the orientation on an edge, the invariant would only change by a sign. So if I consider an oriented graph as an equivalence class of these things, modulo those relations, then it's a fact that oriented graphs give me a basis for the invariance of the exterior algebra. Yeah? Oh, I'm sorry. Right, I was going to deal with this. Okay, so that's how you get that's how you identify graphs with invariance in lambda in this big exterior power. And we wanted to do that, remember, because we wanted to compute homology. We're going to do it by looking at the invariance. And here's but now we have to figure out what the boundary operator is. So what do you have to do on this invariant? You need to bracket all of the monomials that occur at all the different vertices in every possible labeling in that big boundary, that sum of boundary operators. We have to do lots of brackets. So this kind of happens in two distinct ways. You could be smashing together two edges that together make a single, two half edges coming out of vertices that together make a single edge. Or you could be smashing together two half edges that don't make up an edge. So what I'm going to do is collect terms in my boundary operator. I'm going to separate the terms that where I'm smashing together two things from the same edge and the things where I'm smashing things from different edges together in different terms. And it turns out that when I do that, when I look at what I have from the things that correspond to a single edge, well, when I smash them, the edge disappears. And what I get looks like a labeled graph on the graph with that edge collapsed. You call that gamma sub E. Then you can compute that the boundary of gamma is 2n times the invariant associated to gamma sub E plus some other stuff that comes from the other smashes. So the other stuff we'll call boundary sub E. It's not going to work. Okay, so that's how we compute the homology. That's what the boundary operator is. You can now take graphs and compute its boundary operator. Terence has done a lot of computations of that. So, but now we wanted the homology is C infinity, so we want to take a limit. So we want to see stably what happens. So if you stick this algebra inside of the next one, you allow labels up to n plus 1 instead of just n, then the inclusion is a chain map, so you get a map on homology. And Kontsevic's theorem actually says that the limit as n goes to infinity of these homologies is exactly the homology of the chain complex of graphs, which was luckily described in the last lecture, but it was 2 hours ago, with this boundary operator. So you get a chain complex of graphs, you get a basis element for every graph.
Well, the only distinction even between
Right.
idea work.
Same idea.
Planar versus abstract.
Well, this one I'm talking about abstract. If I'm talking about AN, I'm talking about planar. Otherwise, if I'm talking about LN, I'm talking about Lie graphs. Okay, so there's one little problem with this that we had a hard time with when we were trying to figure this out. So what we want to take is this limit as n goes to infinity. Now we've identified the homology of Cn with this graph complex, and we want to take the limit as n goes to infinity. But that boundary operator depends on n. If you remember, there was a 2n in the formula for it. And we want to take the limit as n goes to infinity. So what do you do? Well, here's the inclusion map as I gets bigger. If you just look at the subcomplex of invariance, it's just not true that the subcomplex of invariance is included into the subcomplex of invariance when you go up. These guys, when you stick them up here, are not sp2n plus 2 invariants. So the inclusion map here doesn't form a commutative diagram. Well, we've identified these invariants with graphs. And there's an obvious map from graphs with K vertices to graphs with K vertices. Problem with that is it's not a chain map. It doesn't commute with the boundary operator. So we don't have a map from graphs with the boundary n to graphs with boundary n plus 1. So we were stuck. There's a solution. I only have 5 minutes. You're not going to see it. What I want to do now is go back to this error term. The difference between boundary G and the Lie boundary operator and this boundary G, which Kontsevich uses to compute the homology of this complex, which just collapses edges one at a time. That's boundary G. Okay, so I want to think about this extra term that comes in here. And Jim noticed that there's a nice way to organize this. If you have two edges, you've got 4 half edges that you can smash when you feel like it. For instance, you smash the top half of E with the bottom half, with the top half of F. I've drawn a picture of what happens. When you do that, however, you've got these 2 dangling half edges, but luckily they've got compatible labels. So we'll think of them as a single edge, labeled with the PQ. So we get starting with an oriented labeled graph, we're going to get a new oriented labeled graph over there, which I'm calling minus gamma of E plus F plus. So I can do this in 4 possible ways. I've got 4 half edges to play with. So I'm going to define gamma sub EF to be the sum of the terms I get by doing all the possible smashes. Or in pictures, I'm going to denote this gamma sub EF by a dotted green line between E and F. It means the sum of the 4 graphs you get by doing these 4 smashes. I haven't bothered to smash them here because it's hard to draw, but the red ones get collapsed. Okay, so if I collect terms in that way, then I get this nice description of what boundary E is. Boundary E of gamma is just the sum of all pairs of edges which aren't the same of these gammas of EF, these 4 terms. So here's a lemma. If I do that one, then that one, I get minus doing that one and then that one. If I do that one and then do that one in all possible ways and add those up, I get 0. And Jim used this to show that boundary square E is equal to 0. So boundary E is, in fact, itself a boundary operator. But when he showed us this, we said, hey, you've got the Jacobi identity. So we sat there. It's a Jacobi identity. Since this is a boundary operator and all these guys are boundary operators, you also get the boundary sub E commutes with boundary sub G. So what do we really have? What we really have, next thing we want to do is take 2 graphs and do this operation on them. And that's going to turn out to be a bracket. So you take the disjoint union of these graphs. If you had graphs numbered 1 to K1 and 1 to K2, you bump up the numbers on this one so that you have a graph with edges numbered 1 to K1 plus K2. And you get this relation. And you define the bracket like this. Maybe in pictures, the way Dennis was drawing these things looks better. Here's gamma 1, here's gamma 2. You look at all the edges, E1 and E2, and take all possible pictures like that, and that's going to give you a bracket. If you put the appropriate sign, then you get a graded anti-commuting relationship and a graded Jacobi identity. I think I'm going to do this. Okay, I want to explain how bracket interacts with the boundary sub E. So if you do this computation, I mean, this is the same, also the same picture Dennis had. If you want to bracket two disjoint graphs, then, well, sometimes, if you want to take boundary sub E of two disjoint graphs, sometimes you're taking dotted lines in the same graph, sometimes you're taking dotted lines across the graphs. The dotted lines across the graphs are the bracket. So what boundary sub E bracket is it measures how far the boundary sub E is from being a derivation. In contrast, boundary sub G really is a derivation. And you can put these two facts together with the fact that the boundary sub E and boundary sub G anti-commute to prove this little lemma, which shows that bracket takes cycles to cycles and it's well-defined modulo boundaries. So actually, bracket induces a super bracket on the graph homology itself. Super Lie bracket, yeah. And a couple of remarks. What Koncevich, how he actually defines graph homology in his paper is you only look at connected graphs. So you notice if you bracket connected graphs, you still have a connected graph. So you get a bracket on this primitive homology, which is the direct sum of his graph homology as he defined it. And a similar analysis of A infinity and L infinity should give brackets on the primitive homology of the other algebras. These guys are identified with the cohomology of the mapping class group and the cohomology of out of Fn. So what we have now is a super Lie bracket on those cohomologies, all stuck together. And finally, I went to Georgia and learned what a co-bracket was. Dennis drew these pictures, and someone Xeroxed them who wasn't a mathematician and said, I got these pictures of bird tracks for you. And so these other guys already knew what co-brackets were. But here's a remark. If you start with a connected graph and do this boundary sub E, well, some of the terms aren't going to be connected anymore. So sometimes, for instance, if you have a graph that has two edges, which if you remove them would disconnect the graph, then one of the terms you get looks like this. You've got, well, one of the terms, you collapse this red thing to a point, and you don't do the other one. So the result of the bracket is a disconnected graph. So basically, this observation leads to a co-bracket from graphs to graphs, tensor graphs. I didn't put in the signs, so I didn't think you would actually, well, they're there. Jim claims they're there. And this is compatible with brackets, so it gives a Lie bi-algebra structure. And that's my time.
So the final result is really independent of the same respect to the same set of graphs and the structure of the biology.
Yeah. The Koncevich discussion is a motivation
Right.
to show that this thing comes up naturally when you're thinking about the algebra cohomology. In fact, as you know, the fix that I didn't show you was forget about Lie bracket homology, think about Lie bracket cohomology. So Dennis suggested this, and the next day Koncevich sent us an email saying, forget about the homology, think about the cohomology. So he's got good instincts.